friends, welcome to video lecture on dynamics of machinery. In the today's lecture, we'll discuss about numericals on free undamped single degree of freedom system. So let us start the first numerical on the same topic. A uniform rod of mass m is supported as shown in figure. Determine the frequency of the resulting motion. The system is given like this. Okay, so here the one cylinder rod is here. Rod is pivoted at this point, and towards one end of this one a spring is connected at the end of this rod, and the spring is fixed at the another end, and stiffness K. So here the dimensions of these rods are given. From the center of this one, L by 2 length is given with us, and here L by 2 length with us. Okay, so if I pull this rod, okay, in downward direction, so what will happen? The displace diagram or the free body diagram of the system will come like this one. This is nothing but the original position of the rod. Okay, just show the displaced position of this rod. In this way, here is the pivot point. So because of moment of this rod on this side in downward direction, the spring get compressed like this one. Initial position of the spring is here. So the compression of this spring takes place by distance x. Okay, and the length, this one, L by 2 and L by 2, this will remain as it is. At the same time, just show the another forces. So the moment of this takes place rod like this one, in this way. So what's about this one? This indicate the accelerating force of the rod. Okay, so what's about this angle theta with us? What's about this one, accelerating force? Easily we can solve this problem with the help of Newton's second law of motion. So from Newton's law of motion, okay, what's about the Newton's second law of motion? Summation of accelerating force equals to summation of external forces. First of all, identify the accelerating force. Here is the accelerating force, okay, whose magnitude I into theta double dot. Okay, so what's about the next one? The spring stiffness with us K. Spring get compressed in downward direction, automatically it's a resist for the compression in upward direction, whose magnitude with us. So spring stiffness with us K and displacement with us X. So what's about the spring force Kx with us? So if I take the moment of this spring force about this point, okay, O point is here, you have to take the moment of this force about this point. So what's about the magnitude Kx with us? This turns about this point in clockwise direction. For clockwise, you have to use the minus sign. So what's about the spring force Kx multiplied by distance with us L by 2. Okay, so apart from this one, no any force with us. Okay, so what's about the next step? Just simplify this one, I theta double dot plus Kx into L by 2 will come here, equate with the 0. So at the same time, get the relation between this theta and x from this small triangle form here. Here is the small triangle with us. From this one, I can get the relation between for x and theta for smaller angle, get this relation x equals to L by 2 into theta. Okay, so L by 2 into theta, how this actually comes? If I consider this triangle, okay, so tan of theta equals to this side divided by this one. So angle is very small, we can consider that tan theta equals to theta. Okay, and we can get this relation x equals to L by 2 into theta. So from this relation 1, just replace x equals to L by 2 into theta. So from equation number 1 will be modified like this one: k into x with us L by 2 into theta. Again this L by 2 will come here, equate with the 0. Okay, simplify this one: I theta double dot plus k into L square divided by 4 into theta, equate with the 0. Okay, now for the slender rod, for a slender rod, we know I is nothing but ml square divided by 12. Now replace this I, I'll just continue this one here, ml square by 12 for the I, theta double dot, just continue from this step. Okay, plus k into L square divided by 4 will remain as it is, equate with the 0. Now write this equation this way: L square by 4 into theta, this term goes in denominator, okay, to 0, equating this term with the SHM equation, equating with SHM equation. What do we get here? So instead of writing it is SHM equation again and again, you can just write this in this way, equating with the SHM equation, and write here direct omega n square root of, simply write this term direct, this one, k L square by 4 divided by ml square divided by 12. Okay, so in this way step will come. Again, if you just simplify this, so I can simplify this: square root of k L square by 4 multiplied by 12 divided by ml square. In this way L square this term. Okay, so we can get square root of 3k divided by m in terms of radian per second, and just get this value in terms of hertz. The equation of relation will be like this one: 3k divided by m upon 2 by 3k divided by m. Let us start next problem. A uniform rod is restrained to move vertically by both linear and torsional spring as shown in figure. Calculate the frequency of vertical oscillation of the rod. Assume the mass of the rod as m. So in this case, linear spring as well as torsional spring is involved. Our aim is to find out the vertical oscillation of this rod. So first of all, to draw the displacement diagram, or we'll just say here the free body diagram for the given system by showing all the forces. If the rod move in downward direction, automatically the spring get compressed. Okay, like this one. I'll just make the changes in the original diagram so that you can get where the changes will occurs. So here the displacement by distance x will come, small angle with us theta. So when I pull this one, so whatever the spring energy stored here. Okay, so the tendency of this spring to oppose that direction, okay, by the magnitude here kt, the spring stiffness for the torsional spring with us kt, and here displacement with us theta. So kt multiplied by theta will come for this case, okay, spring force. What's about the next one? So here the k with us displacement we can get in terms of x, okay. So I'll just consider this spring force offered by first spring is nothing but the S1, and by the second spring is nothing but the S2. When the spring get expanded, so automatically the direction of this one will comes here. Okay, this is the direction of spring force S1, and if you just look towards this one, second spring, the spring get compressed. The tendency of the spring also get here expanded. So again the direction for the second force, that is S2, will come in the same direction. Okay, so by using Newton's second law of motion, we can solve this problem easily. For that, just go through the various steps. First of all, just let the bar is given an angular deflection theta, like this one as shown in figure. This results spring moment deflection x. Okay, the spring force due to springs 1 and 2 will be S1 equals to S2. Why I'm saying the S1 equals to S2? Because here the stiffness given for this spring is nothing but K. Here also the stiffness is given same, okay, K. That's why S1 equals to S2 equals to stiffness for this one with us K, and the same displacement takes place or deflection will come here, that is X, okay. The direction is also shown, spring force directions are shown here, okay, in the vertical direction like this one. Now the important step here, our next step is to get the relation between this theta and this one x. For that, for the smaller angle, again I can get the relation between x and theta. Just consider this triangle, okay. Let's just consider this one O, this one, this spot and this point, okay. What's about this x? X is the thing, but here this length with us L, so you can get L into theta, okay, for the smaller angle. So just focus on the various forces and here apply Newton's second law of motion. From, I'll just start this from here, from Newton's law of motion, here we can get accelerating force equals to summation of external forces. Now focus on the accelerating force. Here whatever the moment of this one is shown in this way, okay. So what's about its magnitude? I into theta double dot. So this I is nothing but the mass moment of inertia of this slender rod. So what's about accelerating force? Now see here, this one turns about this point in this one, just look towards this force carefully. This turns about this point in clockwise direction. So as per our notation earlier, we have considered what are the moment because of the anti-clockwise forces. You have to consider that as negative. So minus I into theta double dot equals to, just focus on the external forces. So external force start from here, kt into theta, okay. So this actually kt into theta is about this point. Okay, so the distance here and the this one k to theta, this term you have to consider as it is. Okay, so kt into theta, this turns about this point in which direction? This one in anti-clockwise direction. So consider this one as positive. So next one with us here, this turns about this point in which direction? Again in anti-clockwise direction. For anti-clockwise, just consider this one S1. This is nothing but the spring force. We are assume, okay. Multiply by distance with us, a length for this slender rod with us L. Okay. So S multiply by, so what's about this one? S1 multiply by L. Okay. So again for the second spring, the same direction. This turns are also about this point in which direction? In anti-clockwise direction. For anti-clockwise, you have to consider the positive sign. This one positive sign. Okay. So what's about this one? Again, you can get S2. S2 multiplied by this length with us L. S2 multiplied by L. Since the value for S1 and S2 with us, K into X, already this one with us. Just substitute this one, K, S1 and S2 equals to K into X here, okay? And just simplify this equation. Minus I into theta double dot equals to kt multiplied by theta. This term will come as it is, plus s1 means k into x into L, plus again this s2 means k into x into L. Okay, equate with the 0. Now take all the terms towards one side. If I take all these terms towards one side, so everything become positive. Okay, x L plus xl equals to 0, like this. So in the next step, try to simplify this. What's about this x? Already we have seen x is nothing but L theta. Easily you can replace this x by L theta and can bring this equation in this equation in one variable, that is theta. So I into theta double dot plus kt into theta plus k into L theta for x multiplied by L plus k, here k into x means again L into theta into L will remain as it is, equate with the 0. This term is twice time, so you can simply write this in this way, kt. Before that you can take this theta also common, kl, this one kl multiplied by L square. Okay, this one L square into k, theta okay is here, and L multiplied by L square. You can simply write this like this, kt plus k 2k L square into theta equate with the 0. Okay, so therefore I theta double dot plus kt by 2k L square divided by I into theta equals to 0, like this. So in the next step, for slender rod, for a slender rod, we know I is nothing but L square divided by 12. So this I is about center of gravity point, that is, you can just consider this one as Ig. Okay, so my target is to get the value for this one, this I. So this can be found out by using a parallel axis theorem, okay, easily. So I about its end can be found by using parallel axis theorem. What's about this theorem? I equals to Ig plus mh square. Okay, so here h is nothing but half of total length of this slender rod. Already we know Ig is nothing but ml square divided by 12 plus, what's about this h? So h is nothing but here L by 2, or here L square divided by 4. Okay. In the next step, we can easily get the answer for this. So what's about this one? Make the base common for this. Get like this one, ml square. I can get this one. Make the base common for this one. If I multiply by 3 term here, okay, and 3 term here, what we get here? 4 ml square divided by 12, or simply we can get ml square divided by 3. Okay. So from this equation, just erase this portion and continue from this side. So this is about the I. Okay. So this equation with us, theta double dot plus kt plus 2 into L square divided by I with us 3 ml square by 3, like this. Just simplify this. Theta equals to 0. You can get theta double dot plus, this term comes into numerator. You can get 3 into kt plus 6 into k L square divided by 3 into m L cube, like this, into theta. Now our task become very easy. Compare this equation or equating this equation with SHM equation. You can get a direct answer for frequency here. So this term is nothing but here get omega n equals to square root of this term indicate k by m. M means here this term indicate the direct omega n equals to 3 kt plus 6 k L square divided by ml cube. ml square actually. This term is ml square. Get this one in terms of radian per second, and frequency in terms of hertz we can get by multiplying 1 upon 2 pi to this term ml square in terms of, for the answer.